Welcome to Web Handling. My name is Dave Roysum. I am very excited to continue this series on the economics of web handling. In this clip, we are going to show you how to analyze a very complex problem with almost no information. In this example, we are assigned the job of finding the optimum flow rate of water through a non-woven web washer. We will do this even though we know almost nothing about the web or the web machine. We will do this even if we don't know what a non-woven is or what a web washer is. We will do this without ever even seeing the machine. In other words, over the telephone without the benefit of so much as a diagram or picture. Also, you are only given 2 data points of information. Sounds impossible? Not really. Not if you understand that many problems like this have a similar pattern or structure. When you recognize the pattern, you will know exactly what questions to ask and what to do next. However, to make this a bit easier to imagine, we will describe the machine as a roll-to-roll process with a water washing cabinet in between. The flow of the water in the cabinet can be adjusted. Thus, the diagram below is adequate for this purpose. Any more detail will be distracting. The first data point we get is that as soon as the water pump is turned on, the web starts to wrinkle. So wrinkling is what prompted the call for help in the first place. The customer expects you, as a wrinkling expert, to offer advice on spreaders or whatnot. However, that is not the place to start. We may go there eventually, but not now. Right now, we can conclude that the web machine is okay without water flow, but water flow initiates wrinkles. The second data point comes when you ask the customer, why not just turn the water off if it is harmful with regard to wrinkling? You can guess, but let us spell it out clearly. Without water flow, the lint you want to clean off the fabric does not get cleaned off good enough. They have a quantitative lint test that may require the nonwoven to be rewashed if there is too much lint remaining on it. You immediately see that flow is helpful as a process element. However, at the same time, flow is also hurtful as a web handling element. In short, flow is both good and bad at the same time. We see this pattern all the time with knobs and adjustments and parameters on our machine. In other words, a common pattern, but just not on a web or a web machine you are familiar with. No problem. We know how to proceed anyway. There is one critical question to ask for situations that have this pattern of a knob being both good and bad at the same time. It is not what the web is. It is not the speed, tension, or any other setting on the machine. It is not the make and model and age of the machine. All questions about details like this are distracting. They hide the essential pattern with data noise and, as a consequence, slows the problem-solving process, perhaps to a complete halt. The question to ask is, in this specific example, is how often, at the current flow rate, do they currently fail a lint test and have to rerun or rewash the fabric? The answer the customer gives is Never. The reply you give back is to turn the flow down. In other words, you now know that the flow rate setting is not optimized. All costs are at the high flow rate, in other words, wrinkles. There are no flow rate costs, in other words, rework. If you want, you can, in your mind or on a piece of paper, construct the cost curve for this system based on flow rate. The high flow rate defect, wrinkles, starts at or near zero, is concave upward, and goes to infinity on the high side. We've seen this pattern before, have we not? The low flow rate defect, rewash, starts at infinity and goes low, or perhaps to zero, on the high side. We've seen this pattern before, have we not? We sum the cost curves for the high and low flow rate defects and then plot current operating conditions as a data point. As seen here, the system is way out of balance with regard to high and low flow rate costs. Way too far to the right. Back off on the flow before you do anything else. Do that now. We have seen this economic pattern before, where one knob, say flow rate in this example, is both good and bad at the same time. Our first move is toward getting the high and low flow rate costs about equal. We can do this with almost no information about the process and only 2 data points. After we do that, then we are in a great position to see if the now economically optimized process is now good enough. It is possible in this example that moving flow down to 200 or 100 gallons per minute might yield no wrinkles and no rework. If not, we will have to redesign either the web or the web machine. Thank you so very much for watching this video on yet another example of finding the economic optimum for a process. So what happens if the economic optimum is not good enough? Why do we often get stuck? Stay tuned as we answer those and other questions in the next upcoming clips.